Hey, this is Mr. Boggs, and today we're talking about electricity. So if you've ever been shocked when you've touched a metal doorknob or say the outside of a car or something, that shocking experience is due to an electric charge. And so to figure out why that happens, first we have to talk about positively and negatively charged particles. And so here we have a brick. And a brick is made out of matter, so matter is anything that has mass and takes up space. But if we magnified that brick down to its basic parts, we would find that it's made up of atoms. And atoms are made up of subatomic particles, and those different particles are the protons, which are positively charged. And they also have neutrons, which are neutral, and they have no charge. And so that's what makes up the nucleus, is the protons and neutrons. On the outside, in the electric cloud, we have negatively charged particles called electrons. And so usually in a typical atom, you're going to have the same amount of protons as you have electrons. And so what's going to happen to the charge on that atom, they're going to eliminate each other. And so you're going to have a neutral atom where you have no net charge. You're going to have the same amount of electrons, same amount of protons. But every now and then you can lose some of these electrons. It's a little harder for an atom to lose its protons, so most of the time it's going to be a transfer of electrons that gives an object or a material a charge. And so let's talk a little bit about how those different particles react whenever they get close to each other. If you have a positively charged particle and a negatively charged particle, those particles are going to be attracted to each other. And so opposite charges attract. If we have particles that are the same, we have a negative and a negatively charged particle, or electron and electron, or a proton and a proton. Those are going to repel each other. So like charges repel each other. So keep that in mind whenever we're talking about the behavior of electricity. Remember that like charges repel, opposite charges attract. And so if you've ever seen a balloon stick to you, that's because of static electricity. And so static electricity is the accumulation of excess electric charge on an object. And so if I had a balloon here, how could we get an excess of negative charges on it? And so if you ever rubbed it on your hair and it stuck to you, so I could rub this on my head here. Of course, I don't have a lot of hair in this, it'd probably work better, but I can actually feel the static electricity building up. And so this illustrates the law of conservation of charge, and that states that electric charge can be transferred from one object to another, but it can't be created nor destroyed. And so now we have a negatively charged balloon, and my hair is now positively charged. And so you've probably seen it before. Now it'll kind of stick to you a little bit. Maybe I can get it to stick to my shirt. It's not really that charged that well. But I can see the hairs moving up and down as I move the balloon, that negatively charged balloon, close to my arm here. And so even though we have a negatively charged balloon now, the total net charge is still 0. And so what do I mean by that? If we added up all the negative charges on the balloon, even though we have more negative charges on the balloon and we have more positive charges on my hair, if we added up the total positive and negatives of the balloon and my hair, we would still have an equal number. And so that's the conservation part of that law. How is electric force like a gravitational force? Well, it's like a gravitational force in that you don't have to, that electrical force, those particles don't have to be touching each other to see the effects of it. So like gravity, if you're falling through the sky, gravity of the earth is pulling down on you. Even though you're not touching the earth, you're still feeling those effects. And so same thing with And electric force, that static electricity, you don't have to be touching the hair to see the effects that it has on it. And so, also like the force of gravity, the distance between the two objects affects how strong that force is. And so if we have the balloon close to my arm, you can see the effects, but if you get further and further away, you can't see those effects any further. And so that's another way that it's like gravity. One way that it's not like gravity is that electric forces are a lot stronger than gravitational force. So with electric forces, you can have just a little bit of electric force, and you can see those results. With gravitational force, you have to have a lot of it in order to see those effects. In other words, you got to have a really big object to see the effects of gravity. And so, and a really big object might be the Earth. And so, compared to the Earth, you can have a really small object and still see the effects. But with gravity, you have to have a really big object. So the gravitational force between me and the balloon here would not be large enough to really see those effects. And so electric forces are actually trillions and trillions of times larger than gravitational force. Ways that you can charge different objects. We have charging by contact, which would be the rubbing the balloon, two objects actually touching each other. And then you can have charging by induction. And so that is just when a charged object gets close to another object or a neutral object, it causes it to change the charge that it has. And so if we look at the balloon on here, as it gets closer to the sweater, what does it do? Sorry. Let's let this fade away here. What does it do? It causes the sweater to be charged on one side. Same thing with the wall on the other side. And so whenever you get that balloon that's negatively charged close to the sweater, it pushes those negatively charged particles away and attracts the positively charged particles on this side. And so you have one side of the sweater is positively charged, one side is negatively charged. Same thing with the wall here. You create the same effect there. One thing, once you have a large buildup of static electricity, it can result in a static discharge. And so that's whenever that electric charge is transferred from one object to another object. A thing to keep in mind is that some objects are better at allowing that electric charge to flow through it. And so we call those conductors. And so a conductor is just a material where the electric charge flows easily. An insulator would be just the opposite of that, where electric charge does not flow very easy. So just to and so some examples of that would be if you ever try to touch a metal doorknob and it kind of shocks you, what's happening is those electrons are transferring from your hand to the metal door. Electricity is also a good example of static discharge, and so that you can see that here. You can see it's actually looks like it's striking the building, and that's because it is striking the building actually. But let's kind of give you a quiz on how well you know what things are good conductors and what things are not good conductors. So the first thing would be your skin, and so is your skin a good conductor or is it an insulator? And in fact, skin would actually be a pretty good conductor of static electricity. And so if you touch a doorknob, you have that charge on your finger. So if you ever run your feet across the carpet, your body may become electrically charged, and then whenever you touch a material that is a better conductor than your hand, you'll transfer those electric charges to that. So what about glass and a glass window? So if you had that same charge on your finger and you touched the glass pane, what would happen? Probably not much, because glass is a pretty good insulator actually. Copper, so this is a copper coin, but actually the wires that wire your house are made up of copper, unless you have some old wiring, which I have in my house, which I need to get rid of, that's made out of aluminum. Aluminum has a little bit higher resistance, so it builds up heat easily, and it can actually result in a fire, which is kind of bad. So, but anyways, copper is actually a good conductor of electrical charge. And in fact, metals are probably one of the best conductors of electricity. What about plastics? Plastics are going to be an insulator, and so we put those around wires to keep from that electrical charge to either being transferred to your hand or any other material that it might not be good to have that electrical charge on. Electricity are the lightning bolts. So lightning is a pretty cool display of static discharge, and so you can see if you have a tall building, you actually have to put lightning rods on top of it, and because electricity is going to find the fastest way down to the ground once you have that buildup of static electricity, it might strike the tall buildings anyway, so they're just giving it a path to the ground. So this lightning rod here actually has some type of wire that goes all the way down to the ground and lets it go safely to the ground. Otherwise, it might go into the building and actually cause a increase in electrical power and might fry all your electronics. So it's good to have those lightning rods on top of the buildings there. Oops. Let me go through this real quick. The difference between static electricity and electric current. So you're probably familiar with both of them. Electric current is what you use in your house to turn on the lights and power your electronics. Static electricity is just that. It's static electric charge. And so when objects have a buildup of electric charge on them, that's known as static electricity. Electric current is just the flow of electric charge in one direction, and so we use wires and things like that, and we can create circuits to create this flow of electricity. And so a battery, and how do we do that? A battery creates a difference in voltage, and so on the negative side you have negatively charged particles pushing or repelling other negatively charged particles in the electrons in the wire in this direction, and then the positively charged particles on this side are pulling those electrons down that path. And so whenever you have that flow of electric current, you can actually power light bulbs and things like that. So it goes into the light bulb, and then it has some resistance in the light bulb, which causes it to heat up and actually light up. So that's the difference between static electricity and electric current. And so hopefully this video helps you guys out a little bit, and then we'll start to get into circuits and things like that, and also voltage and current and resistance. So I'll see you next time.